Before we can get to the holographic universe, I got to talk about a subject, an introduction to it, related to the holographic universe, and it is this word field. What in the world is a field? And some people believe that field is a physical object. Okay, and this fellow raised the issue, and so what I can do is just try to answer his questions. But it starts with an article that came out, okay, and it says, "Is the universe a hologram?" Okay, and here it is. Okay, Scientific American, is our universe a hologram? And so they're celebrating lately, right, the 25th anniversary of someone creating this holographic universe. Okay, and again, we have to go first and look at a field to understand what a field is before we can go into the word, into the holographic universe, because as you will see, they're related. In fact, the word field and the word energy cannot be stripped out of mathematical physics, meaning out of the mouths of everybody out there. Everybody talks in terms of fields and energy, and they don't have the slightest clue what they're talking about. And they treat these words as physical objects. Okay, so here's this fellow, and he says the following. This is what got me started on this thingy. Okay, he said, "You say only physical threads make any sense." Well, no, I'm not saying that they're the only ones that make any sense. We make an assumption, and we say, okay, let us assume that there are ropes out there made of threads, twine threads, and based on that assumption, right? You create your theories. You found your theories on those assumptions. That's the way the scientific method works, okay? That fields are only concepts. Absolutely. Field is a concept. It's not a physical object. You can't use it as a baseball bat. You cannot use it as a thing to move things along or to interface with things. And this is what this poor fellow doesn't understand. Your ropes are said to be physical, right? Yeah, physical. Physical means object, thing. That's what physical, they're synonyms, okay? It's an entity. All these words are synonyms. What is physical? That which has shape. Okay, that's the definition of physical. Ropes have shape. If you don't believe me, go to your local hardware store, ask for a 2-strand rope, and they'll give you something that looks more or less like this. Okay, and this is a thing. Can you see the shape? Okay, it has shape. Okay, so ropes have shape. And what we're saying is that the light and gravity are mediated by an entity that has the appearance of a 2-strand rope, twine 2-strand rope, a DNA-like object. That's what we're saying. That's our proposal. That's our assumption. Okay, so we showed the object. We're saying it's an object because it has shape, and we're going to use it to explain gravity and light. Okay, that's how it works. Okay, well, this fellow said, well, field is also physical. Well, no, it's not. And the problem here is that he hasn't defined physical. He doesn't know what the word physical means, and he hasn't defined it. And the problem there also is that, you know, if you say, look, you got to define these words, they'll say, oh, you're doing word wizardry, you're doing ontology, you're doing stuff that has nothing to do with physics. That's the way they look at it. For them, the word enters in one ear and comes out the other because there's nothing in between to stop it. Okay, there's nothing there. And yeah, you got a problem, because if you think that a field is a thing, if you think that a field is physical, if you think it's an object, then you got real problems. Okay, so we have to determine the words here, because science is 150% word wizardry, word salad, ontology, semantics, any of those words that you dismiss as, oh, that's nonsense, we don't care about words. Yeah, we do. In science, we do, because we have to make ourselves understood to the person who's listening. Okay, we need to understand what your theory is. We won't understand it if you don't define these terms. So when he says it's physical, he's not saying anything, because he hasn't told us what physical means in his world, in his little mind. Okay, you can call it whatever makes you happy. I don't care. He thinks it's a question of naming it. Well, you can call it Susie if you want. You can call it Peter. You know, Johnny. What name would you like to call it? It's not a question of names. It's a question of what does field mean? What does it stand for? It stands for a concept, not for an object. Okay, field is a concept, an abstract concept. It's a mathematical concept. These people say, no, I see something around the magnet and it moves the iron filing. So it's physical. Yet see and touch are not the criteria for an object. Shape is the criteria to define an object. So they think that because something moved the iron filing, that's something they call field, and they say, oh, it's an object, it's a thing, it's a, what, physical. And then he says, you can't deny its existence. Well, you can't use the word existence, which belongs exclusively to physics, until you define it. Okay, and concepts don't exist. You cannot say that a concept exists in physics. Love does not exist. Okay, data or information does not exist. Okay, you can't say that concepts exist. Conscious does not exist. You cannot use the word exist with concepts. You can only use it with objects in physics, and physics is the science of existence. Okay, so the word existence, the word object, those two words belong exclusively to physics. They don't belong to philosophy. They don't belong to any other discipline. They belong exclusively to physics. So if someone says God exists, I don't care. He stepped the line over into physics. Now he's in physics if he says exists. Okay, now he's got to explain what he means by exist, and then we can follow his presentation. Otherwise, if he says God exists or God doesn't exist, we have no idea what he said until he defines the word exist, let alone the word God, right? So yeah, this fellow thinks that its field is physical and that it exists. And we're going to say that no to both those notions that this poor fellow has. He was brainwashed by maybe the people at the Electric Universe or Walter Russell or Tesla or one of those bozos, you know. Okay, so here we go. Here we have field. Is it an object? Well, this is the rundown. Okay, physical means thing, object, entity. All those are the same words. Okay, in physics, and something that which has shape. Okay, so all these words are the same. Whether you say physical, thing, object, entity, something, anything, all those words mean exactly the same thing. Okay. Field, that which has shape. Does a field have shape? And the answer is no. Field does not have shape. And among things that these people never realize is that field is alleged to be infinite. They say the field extends forever. Okay? So if a field extends forever, it's infinite, as a mathematician would say, then obviously it does not have shape. You cannot draw for me a field because you're saying it's infinite. And if not, you got to tell me where it stops and what the field looks like. And so these people want to do something else. They say, look, the field moved the iron filing, so it touched it, and so because there's touch, it's got to be an object. That's their rationale, if you can call it rational. No, absolutely not. An object, that which has shape, not that which you touch or that something can touch. You know, the moon is not an object because the asteroid touched it, crashed against it. No, the moon was an object before the asteroid touched it. And why was it an object? Because it had shape, not because it can be seen or touched. Okay, so let's get that one right. Okay, and again, the field extends forever. Field is a concept, an abstract mathematical concept. What does it mean? It value at each point in space. What are they talking about? They're talking about numbers and units. That's what a field is. Numbers and units. Was created by Mr. Faraday, this word, around 1845. And he published, he gave a dissertation in 1850, and then he published that dissertation in 1851, where he defines the word field. So what is a field? Well, a field is a region. Field is a region of values, strengths of different kind. It could be magnetic strength, could be gravitational strength. Field is a region of strengths, and what they do is they have a value at each point in space, right, in that region, and closer to the object, the thing is stronger, the field is stronger, the numbers increase, and farther away they decrease. That's what a field is, a bunch of numbers. You can't say a bunch of numbers moves this and moves that. It cannot interface with anything. A bunch of numbers is a concept, okay? And so it's irrational to say that a concept exists in physics. So you can't. So field is not an object, not a thing, and then you cannot say it exists because concepts cannot be said to exist in physics. It has to be an object. Okay. So these are the things that this fellow never learned wherever he studied. Okay, the monastery. Okay, here it is. His theory is essentially that a field moves things, touches things, moves iron filings. So he says it's a thing because it interfaced with the iron filing, it moved it, it put it in the right position, or it moved the charge, or in case of gravity, you know, it attracts you to the earth. So there's something there called the field that is doing something to you. It's interfacing with you. It's touching you. Okay? And so what this fellow is saying essentially is that, you know, you have a concept such as love. Okay? And so people say, hey, love moves mountains. Love moves mountains? Well, maybe that's very poetic. That's good stuff for poetry, maybe literature, you know. But you can't use that in physics. You can't say love moves mountains literally in physics, okay? And so this is his theory, okay? He's saying that love moves mountains, okay? He's going to move a mountain with love. This is how he does the field thingy, okay? So he's saying that a field, meaning this concept, is going to move an iron filing. How do you do that? I mean, if it's like love moving a mountain, a concept that's trying to interface with a thing, okay? Okay, here we have the Earth's gravitational field. And what is that field? Well, you can see that the numbers decrease as you go further and further away from the Earth. That's how we look at it. If you weigh 100 kilograms on the surface of the Earth, the farther you go out, the less you weigh. Okay, and what does that mean? Well, that's the gravitational field that, according to the mathematicians, extends forever. Okay, forever means it doesn't have shape, this field thingy, and all we have is just values that are decreasing with distance. The greater the distance, the lower the value. That's what a field is, just a bunch of numbers that decrease in a region, whatever region you choose to chop off. Okay? So that's our gravitational field. How about the magnetic field? You know, here we have a magnetic field. How far does it extend? For example, the magnetic field of the Earth. What are those lines? Are they made of solid iron or what? You know, I mean, what are those lines? They draw them, and these people look at them and say, oh, yeah, I recognize that. That's the field. What do you mean the field? What is that? What are you staring at? Is that some kind of animal that's got all these hairs pulling out of it? You know, so these people treat these words as things. And in the case of the magnetic field, everybody says it's an infinite magnetic field, and it extends forever. Okay, it extends, it doesn't stop. And so if it doesn't stop, it doesn't have shape. And if it doesn't have shape, obviously it's not a physical object according to our definition. Now, if you don't like the definition, no problem. All you have to do is challenge it. You know, challenge it and propose something that you can defend. Defend your definition of what an object is, what a thing is. You can't defend it, you don't have a case. Okay, so here we tell you what it is. A thing is that which has shape. Very clear. Okay, not a thing that you can. A thing is not that which you can see or touch, which is what this fellow is running with. He's running informally with this definition of see, touch, and he says fields touch things. No, they don't, because concepts don't touch things. Love does not move mountains. Okay. Okay. Here we have Stevie Wonder, Stephen Hawking. You know, and he comes up with his idea of what a field is. He gives you an idea here, okay? He says the following, he says, there must be certain minimum amount of uncertainty or quantum fluctuations in the value of the field. And he's going to eventually use this for his, you know, holographic universe, his black holes, his notion of, you know, how this universe runs. So he's going to use this word field. You can also use the word energy, which is another undefined word, right? And treat it as a physical object. Say, oh, the energy. We transferred the energy. Oh, yeah. One can think of these fluctuations as pairs of particles of light or gravity that appear together at some time, move apart, then come together again and annihilate each other. Okay, so we have particles, they can go apart, right? These particles that they call virtual particles, then they come back, they form a single particle, then they separate again. And one thing that can do that is a black hole, the event horizon. Half of the particle falls in, the other half travels to your eyes. That's a Hawking radiation, right? These particles are virtual particles. What's a virtual particle? It's an ad hoc so-called particle, not even a corpuscle, but that the mathematicians invented because they could not explain what's happening in that invisible world in which they run their experiments, right? These particles are virtual particles, like the particles that carry the gravitational force. He's going to have these gravitational particles that carry the force, right? And he says they're virtual. In other words, these particles appear and disappear constantly, so they can't really measure or detect them, so they're unseeable, untouchable. Okay, so even there you would not be able to use the definition. They're unseeable and untouchable. They appear whenever the mathematician needs them, ad hoc, and they disappear when he doesn't need them anymore, ad hoc again. And they call them virtual particles, which ain't particles anyways. They're just values that they have to put in the equation to make the equation come out right. So they say, well, something happened here that we don't have in our equation. Just put a variable in there. We'll call it a virtual particle. So much value, and then it leaves again. For that split second, we have a particle out of nowhere. God sent it. Particles that carry gravitational force of the sun. Unlike real particles, which ain't particles either, right? Because those are numbers as well. They cannot be observed directly with a particle detector. In other words, these are ad hoc thingies that they invent, and they form this field that they're going to use, gravitational field, magnetic field, electric field. They're going to use it all with particles, which ain't particles, which are virtual particles, which ain't particles either. None of these are particles. Okay? They're not corpuscle. They're just numbers that they put in there. We're talking about concepts, not things. Okay? However, they're indirect effects because they can't do it directly, so they do it indirectly, such as the small changes in the energy of electron orbits in atoms can be measured. So they're measuring the electron. They're saying something happens there, and we think it's caused by this virtual particle that appears whenever it wants to and leaves whenever it wants to. Where does it come from? The vacuum. So the vacuum is made of these virtual particles that are buzzing in there, okay? The vacuum is not vacuum. It's full of, not even full of, it's made of particles. Let's get that right, okay? They're saying the vacuum is made of these balls. We don't know what's between these balls because if it's a little ball, right, little grain of sand, it's got to have something distinguish it from the next grain of sand, the neighbor. So it's not one grain of sand, it's 2 grains of sand. There's got to be something dividing them. What's that something? Well, they never figured it out. They just say these particles come in from the void because they make up the void, right? And again, all these particles are making up the void. That's what they're saying. So when you pull one in, I guess it leaves a hole behind. What does it leave behind? Another space? I mean, I don't know. They have to figure this out. Anyways, here it is. This is a field, okay? And I want you to see this because when you have a field, what is a field? We're saying that a field is a bunch of threads that are magnetic field, right? A bunch of threads that are spinning around the atoms, okay? And so that's a field. Field has to do with all these threads that are swinging around the atoms. That's region of what we call magnetic field, has something that's moving in there. The field itself is the region, but there is an object there that is moving inside that region. That's the one we have to locate, okay? And here, let me give you a little simulation of what I'm talking about. Look at this, okay? We have the little girl, okay? Her name is Susie, and she's skipping a rope, okay? Now, we have a rope, and we have that red region, and we'll call that a field. That's the field of the rope. That's the extent where the rope is moving, okay? Now, what happens? Field is the region, the red part. And the rope is something else. The rope is the thing that's moving inside that region. So we have the field and we have the object. Field is a concept, okay? It's just a region. Region is a static concept. Now someone throws a stone at Susie. It turns out it doesn't hit her because something prevented the stone from hitting Susie. So what was it? Was it the field or was it the rope that hit that stone that prevented the stone from hitting Susie? Again, was it again here? Field. We have the rope. Okay, and here she goes. Okay, someone tries to throw a stone at her. Okay, or several stones, and as soon as the stone gets near her, something hits it. Okay, something strikes it. Is it the field or is it the rope? Can you say that the field is what hit the stone? Okay, so this is the same situation with the magnetic field. Magnetic field has something twirling inside it, something moving in there. Okay, that's the one that moves the iron filings and all this other good stuff. It's not the field. The field is the whole region of numbers. So the field is a concept. You can't say the field does this or the field does that. You cannot put an article in front of the word field. You cannot say a field or the field. It's irrational in physics. That's okay in ordinary speech. You can talk like that over there, no problem. In irrational language, nobody bothers. But in physics, you cannot put an article in front of the word field because it's not a physical object. You can only put articles in front of object. You can say the chair, the tree, the rock. You can say it like that. And here we have to say, in this case, we say the thread. Thread is an object, and the thread is moving, okay? And the region in which it moves, that's the concept, the abstract concept, the region known as field. Bunch of numbers. It just says it's stronger over here and weaker over there. That's all we're saying with the word field. Okay, because field is not a thing. It doesn't have shape, especially if it's an infinite field. If it stretches all the way to eternity, well, then it cannot have shape. And therefore, it doesn't even qualify under our definition, and it doesn't qualify under the see-touch definition because the field is not hitting the stone. What's hitting the stone is whatever's twirling inside the field region. Okay, we got that? Okay, so here we have good old Faraday who confirms what I just said. He says, I cannot conceive curved lines of force without the conditions of a physical existence in that intermediate space. Okay, he wrote that in 1852. And good old Maxwell, he says, field, the space in the neighborhood of the electric and magnetic bodies. In that space, in that region, right, there is matter in motion. Something is moving in the region, in the concept, in the numerical concept, right, called field. So field is not an object. Something is moving inside the field. And what you got to identify is that something. You cannot say that, what's happening here is that the field is doing something. No, field cannot do anything because it's not a thing. Okay? So here we have proof of that, okay? He said there's something moving inside the field. And I've shown this before. Here we show it one more time so that everybody can kill their ignorance. Something is moving inside the field, okay? That's what I'm saying. That's what Maxwell says. Faraday is saying the same thing. These guys worked a lot with magnets, something people today don't do. They just repeat whatever the teachers or the professors teach them, or whatever they learn by rote. And here it is. Okay, here's a magnet underwater, and you can see the iron filings are picked up one at a time, slowly, by something that is moving that region of water, which we call a field. Field is the water. Okay, is the region. And something is moving inside that invisible region, and that invisible something has the ability to move iron filings around. You can see the iron filings are coming slowly to the magnet. It's not like they all, it's not a static thing where they're already there. It's pulling one at a time. Something is moving in there, and we're saying it's the threads that come out of extend from the magnet itself, from the atoms that make up the magnet. Okay, so we have this magnet, the threads are moving around, and because of that, they're interfacing with the iron filings, the nuggets, and pulling them in one at a time. So this is in slow motion, right? But you can imagine, water is good, really, because it slows it down. If you did it, out here, it would go and bring all the iron filings together. You would probably not notice anything. If you put your magnet underwater, you'll see that they're picked up slowly, slower than out here in air. And so that's the issue. The issue is that in water you can see it slowly, and you will see that something is drawing one nugget at a time. Okay, something is moving in that region. Maxwell said there's something in motion in that region we call field. Okay, so we got that part. Moving on here. Okay, so we're going to relate this now to the holographic universe. And I got to give you another introduction, another subject to be able to get to the famous holographic universe. Here's the circle, okay? Now, everybody said, okay, I've seen that before in geometry, and unfortunately I have to go through this little basic stuff, just so you see how these people think. Okay, we're going to see how a mathematician thinks, okay, and how irrationally he thinks, really. Okay, here it is. You want to calculate the circumference of the of that circle, and it's 2 pi r. Okay, 2r means 2 radius. In other words, you have diameter there, and you multiply the radius times 2, and you get the diameter. And it turns out the diameter fits into the circle about 3 times, a little over 3 times. Where did we get this? Well, we get it from here. You can take a circumference or a circle, right? And you open it up. Here it is, starts in a second, there he goes. And so you unroll it, and that's more or less what you're going to get, 3 and 14, right? And this is how the Greeks really figured it out. They figured that out pragmatic, doing the experiment, some kind of experiment. They said, okay, if it's 3.14 times, you just unroll the circle. That's essentially it, or the circumference. Okay, so that part they figured out, very early. Then came more ideas on, if you wanted to calculate something, like, you want to calculate the area of a circle. And here they said, okay, you have the circle, which again, by the way, the circle is a plane. That means that the circumference is not the circle. The circle is the whole plate. Okay. And so how do you calculate this? Well, here it is. You want to figure out the surface of a circle. They eventually figured out that it's pi times r squared. Okay, so if you multiply the radius squared times the pi, 314, right, you get the surface of a circle. Okay, so this was their line of thinking. Okay. They started with a circle, with a circumference. They opened it up. They said 314. That's the ratio between diameter and circumference. Then from there, they said, well, what if we wanted to calculate the surface of a circle? Well, you saw it there. Okay. Now here's the area of a circle, how it fits from a physical point of view, you can say. Okay. Let me roll it here. Here it goes. You can see it opens it up. Okay, if you take that area, one way of calculating it, right, and you open up the circle, okay, and you do these fancy things on the triangle, you can figure out the area, and that's pretty much has to match the surface of a circle. Okay, you can see how they more or less do it. Okay, so you can prove it to yourself if you want, but I just want you to see the line of thinking here for now. They went from circumference to circle, then they said, what if we want the area, right? Okay, they were figuring these things out. Then they went to this, they said, what if we have a sphere, right? And they eventually figured out that the volume of a sphere is 4/3 pi r cubed. Okay, so if you want to know what the volume is of a ball, right? A perfect ball, right? Ideal ball. Well, you just apply that formula. See how simple it is? And just have to find out what the radius is, and it'll give you an idea of what the volume is. Okay, here we go with this. This is essentially what they do when they try to figure out the volume. They simply put layer upon layer upon layer until they reach the radius, okay, of the sphere. So this is what they have in the backs of their minds. It's nested layers, nested spheres, okay. If you put one inside the other, you'll eventually end up with the volume of the whole sphere, okay. And there's a neat little trick to find out if you want to turn your volume into the surface, you want to calculate the surface area of the sphere. So you have this, you have this volume in the sphere, right? And there you had the equation. And if you want to calculate the surface now of that sphere, well, they figured out how to do that as well. And here, let me show you how they do it. A nice little trick. So that way you can learn little derivatives and calculus. You'll be an expert after today. Okay, this is what they do. Okay, this is the notion. Okay, what you have is you have the volume of a sphere, and what you do, you take that 3, you put it up front. Okay, and you subtract 1 from the 2, from the 3 there, from the r cubed. You went to r squared. Let me show that one more time. Okay, here it is. You start out with 4/3 pi r cubed. The 3 from the cube goes to 2 and becomes a multiplier. One more time. Okay, here it goes. Okay, look at that 3. Goes out, turns into a 2, and then the 2 3's cancel out, and there you have 4 pi r squared. And that is the surface area. That will give you the value of the surface area of a sphere. Okay, so you have the volume, you have a way of calculating that, and you have the surface area. Bill, why did you go through all this nonsense? Oh, I didn't come here to learn math. I came here to learn physics. Okay, because our holographic universe has to do with what you just saw. That's why. The idea, the notion they have is that the surface area, okay, of a black hole, right, is coded. In other words, it codes the information that's inside a black hole. And the notion is that our universe is like a black hole. They're trying to figure that out, and they're saying, well, maybe we're inside a black hole, meaning a sphere, right? And if we can figure out, what's on the surface, we can code that and find out what's on the inside of the universe. And if that's the case, well, then you have this holographic universe, which is a way of looking at how a 2D surface, they call it 2D, it's not really 2D, but they call it a 2D surface, projects its, or is a measure of how much information is inside that ball, okay? So why did they do this? Well, because now you're putting a little bit of relativity, which is the black hole part, right? And you're trying to figure out, how we can use some geometry, some regular stuff, and see if we can merge quantum mechanics with relativity. Okay, so that's the point. That's how string theory came to be, and that's why string theory is still alive and well, because they're trying to figure out gravity. They're trying to figure it out from the 2D surface, how it's projected onto the 3D volume of a black hole. That's their starting point. And then they're going to extrapolate that and say, well, the universe is also holographic. And they use the term holographic because, what is a hologram? Hologram is a 3D projection of a 2D surface. Okay, so that's where that's how they put these things together. And again, it's got to do with their line of reasoning. Okay, they're always trying to calculate things. They're saying, I want to calculate circumference. I want to calculate the circle, the surface area of a circle. I want to calculate the volume of a ball. I want to calculate, the surface area of a ball. And when they go through this whole thing, they say, oh, by the way, it turns out that a black hole is a ball. It's a perfect ball, right? Because it sucked all this. It was a star, right, that collapsed gravitationally upon itself, or so they say. And because it's got this region of influence, which we'll call the surface of the black hole, and they're going to say, look, if you want to know what's inside the black hole, all the information that's in there, hey, you just got to look at the surface, because That's what the surface is. It codes whatever information is inside the black hole. Okay, so this is their line of reasoning. That's why all this is tied together. Okay, so here we have a black hole. Okay, it looks more or less like that. Think of it as a sphere. Okay, black sphere. And again, it's important to note that that's not totally true. What you really have is a singularity in the center, and the black stuff is really a region of influence that they call the event horizon. Okay, so you have the little dot in the center, which unfortunately, I have to apologize, I wasn't able to make it zero-dimensional. I tried all night to make it zero-dimensional, and I always kept getting at least 2D. So no matter how hard I tried, I guess I'm not a good artist, but maybe you can try it at home, always in the presence of a relativist, and try to see if you can draw a zero-dimensional singularity. Anyways, that's what's in the center there. Okay, here we have, let's get rid of the words, okay. So you have this, you have a little dot in the center, which is a singularity. You have that surface, right? The red line around, red circumference, right? But it's really, you got to think of it as a cross section there, because what you're really looking at is the whole covering of the sphere. And that whole covering, the whole sphere is really the black hole, or the extent of the black hole. You got to think of it like this. Think of it as a a campfire. So the little dot in the center is the campfire, and the region of influence is, you have heat from the campfire. Well, the region of influence is how far does the heat go, where it has some kind of effect. And so, you're not in the center of the campfire, you're somewhere far away, and you can still feel the heat of the campfire. And this is more or less the same thing, an analogy for that. Here you have the little dot in the center, which is supposed to be 0D, and the region of influence, gravitational influence, where gravity travels at the speed of light, right, is up to that red circle that's going around it, the circumference, okay? So this is the notion of a black hole. Okay, so what's the issue? The issue is we're going to try to calculate the volume of that sphere, and what we have on the outside is the surface area, and they say, you use that equation, and you're going to figure out, how big the black hole is. Okay, and they can do this with mass. They say it's got so much mass. So the volume of the sphere, of the event horizon, right, from the singularity all the way to the edge of the event horizon, right, you can calculate not only the volume, but you can calculate also the surface area that encapsulates that volume. Okay. And of course, if more matter falls in, well, then what you have is a bigger black hole, supposedly a bigger event horizon, right? It expands, and you have to do a new calculation for that new expansion. But the point here is that what they're trying to tell you is that all the information, really, I hate to use the word information because they're saying that information travels. Okay, and again, we're moving concepts here. Okay, make sure you understand that. But they say any particle, any atom that falls into the black hole is sucked together all the way to the center of the black hole, to the singularity. Okay, so now that little particle, right, goes all the way to the singularity and disappears. It's crushed out of existence. What remains is its mass. Okay, and because now the mass is greater, the event horizon now has expanded by so much. And so by studying how much surface area the event horizon has, right, it codifies, it tells us something about what's inside the information that was put into, as they call it, information that is inside the black hole. It's got to do with this word entropy. Okay, they equate entropy with information. Okay, so now we're away from physics. Now we're going to talk about information, entropy, how much disorder there is, how much information there is inside a black hole, whatever that means. How can you contain information? But this is what they talk about. So I can only go with what they're saying. Okay, I can't. I'm just trying to tell you what these people are talking about. That's all. It's all nonsense, but we got to start somewhere. Okay. And here's Mr. Matt O'Dowd, and this is what he has to say. The main part, okay, he says, a black hole's entropy represents the amount of quantum information of everything that ever fell into it. Okay, so he's going to talk about information. He's not going to talk about things anymore. Now he's going to talk about this abstract concept called information, which he probably wouldn't be able to define. And he's going to talk about how much order, how much disorder it has, entropy being the word used for that concept. Okay, this represents the maximum possible entropy / information of any volume of space. Okay? The maximum is proportional to the surface area of that space, not its volume. In other words, what they're saying is the surface area is going to give you an idea of how much entropy, how much information is in there, or something about information that fell in there, together with the particle that carried that information. The information of all material that fell into the black hole could be imprinted on the outgoing Hawking radiation. In other words, you have this Hawking radiation, again, particles that split, and one guy leaves to your eye, the other one falls in, essentially. So they use these virtual particles, again, ad hoc stuff, to explain these things. Well, it's waiting to be radiated. This is interesting. While it's waiting to be radiated, that information should be encoded in the event horizon. So here you have this information, it's just waiting there. Information is just standing there at the event horizon. We have nothing sitting on nothing, right? We have information sitting on an event horizon, okay? And it's waiting to be radiated, still not radiated, but while it's still there, we can study the black hole and say, okay, all we got to look at is the event horizon, find out how much information is sitting there, right? And from that, we can tell something about what's inside the black hole, the history of what happened to that particle, so to speak. That's the information. From the point of view of the outside observers, its contents are smeared onto the 2D surface. Okay, so the surface is painted with all this information. From the point of view of anyone falling in, they are definitely inside the black hole. This is the first glimpse of a holographic space-time, a 2D surface that encodes the properties of the 3D interior. Okay, so what any of this has to do with physics, I have no idea, but I hope you're getting the idea. The idea is that particles fall in, right? They form part of that region called from the singularity to the event horizon. Singularity is zero dimension. It's just the center of this whole thing. And contains essentially all the mass you want, as much mass as you want. And depending on how much mass that singularity has, the event horizon has a certain radius from that singularity. So it gets bigger. The globe gets bigger. The sphere gets bigger. The sphere of influence, okay? And so you have the event horizon, and on that event horizon you have information that's just sitting there, just painting the walls of the event horizon. It's just sitting there until they give them the order to be irradiated out. By studying what's on the surface for that split second or however time, maybe it's an eternity, that it's just sitting there, you can tell something about the particle that fell in, which is the information. And so this is what they're trying to convey to you, that they can, by studying the surface of a black hole, they can tell you something about the information, the entropy, right, that's inside the black hole. Okay, and here you have one article that convinces you that what I just told you has to do with our universe. Our universe is holographic because it is like a black hole. You can treat it like a ball, and because remember, Big Bang, hopefully was quite symmetrical. Space was expanding in all directions, so you would think we're talking about a ball, right? So the universe is a ball. What's outside of it? We don't know. As we talked about last week, we don't know what's outside because they say you don't have to have an outside to a ball to be able to conceptualize a ball or visualize it, right? Okay, fine. So we have nothing outside the ball, but the ball has a radius, okay? And that radius is expanding. Okay, so here it is. Okay, you have, is our universe a hologram? These people are trying to convince you that it is. Much like a 3D hologram emerges from the information encoded on a 2D surface, our universe's 4D space-time could be a holographic projection of a lower dimensional reality. Okay, so now we've extrapolated our our notion of a black hole, what they study for a black hole, and we say the universe is like that as well, because it's so dark. Maybe we're inside a black hole. It's a sphere because you had Big Bang, and maybe the galaxies and the stars, they're all scattered in different directions, but space is quite symmetrical, you would think, and all the galaxies are sitting on the surface of this expanding globe, which is space, right? And so, yeah, if you treat it like that, you say, okay, then I can study the universe as a hologram, because all we have to do is find out, how it's encoded on the surface of this thing we call universe, right? This ball. Here's another one from Popular Mechanics, just to make sure that we cover all the bases. Information is, it says black holes may be evidence, okay? So they're looking for evidence, right? And they also suggest that we are living in they say could be, but they really mean we are, right? Living in a holographic universe. Information is the list of all properties of all the particles that fell into the black hole. In other words, everything you need to reconstruct the original objects that fell in. One way to measure the amount of information is through entropy, a thermodynamic concept that is loosely related to the amount of disorder in a system. Black holes have a surprising property. Which one is that? Their entropy is proportional to their surface area, not to their volume. In other words, the amount of information in a black hole is related to its two-dimensional surface, not its three-dimensional volume, which is what you just said, right? Hologram encodes all three-dimensional information in a two-dimensional surface. Great. So there appears to be something funny about black holes wherein their information seems to be encoded on their two-dimensional surfaces. Perhaps the same is true for what? For the whole entire universe. Okay, so what these people have done, they went from, if we look at the history since the days of the Greeks, we went from circumference to circles to spheres, surface of circle, surface of the sphere. Then they say, oh, by the way, the black hole is a sphere. Okay, so let's put all this geometry that we learn in high school, let's put it into the black hole, and they studied that, they developed equations, and then they said, oh, by the way, we can create a hologram. And what is it? It's a projection of a 2D source to a 3D volume, right? So you see the 3D object in front of you, right? And they say, oh, by the way, the universe is also like a ball because, it expanded from the Big Bang, right? And so we probably can figure out, that the universe works like a black hole, meaning holographically, right? Which means it encodes the matter that's inside the universe, including the space, I guess, from the surface of this expanding Big Bang thingy, space-time, right? So this is their notion. This is how they're working this whole thing. But what's the problem here? Well, at least one of the problems that I want you to carry with you today. And that is, here you have what would happen inside a black hole if the universe were like a black hole. Well, the black hole, what does it do? It pulls everything inwards towards the center, okay? So this is what it would look like, more or less, okay? You would see the universe, right, contracting towards the singularity, okay? That would be what we would expect from a universe if it is like a black hole. And instead, our universe does the opposite. It does something like this, okay? It expands. Okay, our universe is said to be exploding. Big Bang is still exploding, and so it's not contracting towards a singularity. Okay, so these are the notions these people have for the universe, and of course a lot of it is a bunch of nonsense, both the expanding universe as well as the holographic notion that these people have in their minds. They have no idea how this universe works, and all they're doing is math, because they can apply the math to spheres, right, to planes. They say we know about holograms, and it turns out that we can figure out what's going on inside a black hole without going in there, because the information inside is encoded on the outside, on the surface of this black hole singularity. The region of influence stops at the event horizon. We just need to study the surface of the event horizon, which ain't a thingy. It's not a surface at all. It's just a concept. It's like saying that the heat from a campfire, wherever it reaches, whenever it still burns your hand or whatever, you can say, well, it's a thing. No, it's not a thing. The heat is not a thing. Heat is a concept. Okay? The fact that it touches your hand, burns, is a process. But to say that that whole region where the heat is, the field, right, is a thing that you can take and carry with you somewhere, no, it's not a thing. But they treat it as a thing. And if it applies to the black hole, why not to the universe? If the universe is a ball that's expanding with, what's it got on the surface? This expanding sphere, well, it's got all the galaxies, all the planets, because remember, it's not in the volume that we're in. We're on the surface of the universe that's expanding and pushing all galaxies apart and stars, etc. Right? So keep in mind what they're saying. They're saying that the universe is a ball, and all we need to do is study what's on the surface. That's where we're at. We're all on the surface, and that gives us an idea of what's going to be inside, meaning all the way to the singularity, meaning all the way to Big Bang. Talk about the holographic universe. Well, that's what it's all about.